Okay. So we got this situation, we're gonna have an inelastic collision between two masses. I want to know what the common expression is for the common velocity after collision. There's a formula. I'm going to work from first principles. Okay. I want to be sure we understand what the principles are. If the masses are separated then by distance d, what's the position of the center of mass? Want to get a better understanding of what center of mass is. And of course, in calculus, a standard thing in second semester calculus is you do integration to get center of mass. So you should have some intuition about center of mass from second semester calculus. Doesn't mean you do. But maybe just follow the formulas and never really get to the essence of what you're looking at, because that's an expedient way to do it. And you got a bunch of demands in your time, and that's what a lot of people end up doing. Okay. So we want to get to the essence of a lot of that. Okay, well, here we have this. Now, what's the fundamental principle? What is it on your sheet that would be the starting point for analyzing this collision? Now, the basic principle at work here, and people weren't really able to tell me what the basic principle is. People quoted some formulas, good formulas, M1V1 plus M2V2, M1U1 plus M2U2 or whatever, okay? It's a good formula, but that formula didn't get handed down on the stone tablet. Formulas developed from the basic principle, which is what we get when we derive the equations of motion, uniformly accelerated motion, and use Newton's second law, we get the work energy theorem and impulse momentum theorem. Those are two foundational theorems. Okay. And of course, then there's the integral definition of the impulse momentum theorem. That's, I believe I talked about that last time, or if not, then time before that, wrote it all down. Okay. So you want to kind of review that. You want to understand where things come from, and it's not difficult. So the impulse momentum theorem says what? That's when it's derived in your textbook. And we alluded to that. Now, the way we did it in class, we used the equations of uniformly accelerated motion, said if F is constant, if net force is constant, and mass is constant, then we get F net delta T equals M delta V. Assuming F net and M are constant. Because F net and M are constant, M's constant, so you have uniform acceleration. You have uniform acceleration, then you can use a very simple formula V equals V naught plus AT. Plug in F over M for A, we did it. You did it. Everybody did it right. It's so simple you don't remember it. Okay? It's very simple. Everybody got it very quickly. But where is it in your basic scheme of understanding? It's not quite there. Okay, you always go back to that. And at least understand that everything comes from that. Because we can reason this out now totally from that without using any of the formulas that we've memorized and used in solving the problems. And that's okay, those are good formulas. Okay, but we want to understand it as deeply as possible. And what this tells us now, here we have, well, we don't have a constant net force. Okay, if we go back to this, if we have a constant M, then the integral of F net delta T is just F net bar delta T by the fact that the average value of a function is equal to its integral divided by the interval. Which is a short way of stating something a little more complicated, something you should be well aware of because it's very important in applications. So this is what you have for constant M, and this is your starting point. Then, if you have this situation, well, the net force of mass 1 on mass 2 is equal and opposite to the net force of mass 2 on mass 1. So that M the delta T is the same for both masses. Now, implicitly, that's the delta T that occurred during the collision. All these four objects' masses are interacting. Well, it follows that the acceleration of mass 1 which force is acting on mass 1? This one, yeah. Force of 2 on 1. I like that notation. I like the way your text uses it. Okay, I haven't really noticed, does Open Math use that notation? Not Open Math in my lab. So maybe you're not seeing that notation.
I think
Okay, so you have acceleration 1 equals I didn't leave myself enough room for an arrow and a bar. I have to write this one down. There's a bar and an arrow, meaning the average force. And I'll just go ahead and use 2-1, because that's what you're used to seeing. I think we defined what that means. And let's have 2 on 1 divided by mass, right? We have this. This F21 is negative F12, so I'm gonna just choose to write this as F negative F12. Negative F bar 12, average force of 1 on 2 divided by mass 1. So there's this acceleration, there's this acceleration. Okay. Now, can you write down for me? Over delta V1 and delta V2. Okay, seems to be. Okay, so what do we know? Calculate delta V1. We got everything we need here to write the expression for delta V1. Okay. Change in velocity is the average acceleration times the time interval, right? So actually I should have written A1 bar and A2 bar, average acceleration, since we're using average force. Can you use the average acceleration and the delta T to get expressions for delta V1 and delta V2? Okay. Delta V1 is equal to product of the average acceleration and the delta T, right? Which is average acceleration is negative F12 bar divided by the mass 1 times delta T. Okay, so it's F21 divided by the mass times delta T, but we want to, since this is equal and opposite to this, we're going to use negative F1 in both cases. Okay, and delta V2 is a 2 bar delta T. And that's just plain old F12 bar. Keep forgetting to put the bar in there, so it's quite hard to read. Okay. Now what's F12 bar? It's the integral of F12 dt. And what's the length of the interval? It's delta T, right? This is an integral over delta T interval. So that equals F12 bar delta T, right? So this could have been written in terms of an integral. So that the delta V1 would equal what we said it equals here. But what F12 bar is the integral of F12 without the bar is equal to this. And I didn't quite write that correctly, since I was erasing. Okay, F12 bar is this integral divided by delta T, right? Well, I don't have room to write it all out, but if you write it all out, find out what F12 bar is, it's this integral divided by delta T. And like an extra delta T in there, it wasn't working out, but there it is. Okay. Now, what's the integral of F12 delta T, of negative F12 delta T? It's the impulse. That's what impulse is. And that's the change in momentum, which is, in this case, M1 delta V. So that's M1 delta V divided by M1, negative M1 delta V divided by M1, which is just delta V. Delta V1. Okay. Work the rest of it out. I don't have room, but I'm connecting this to the integral. It's well worth knowing because we're dealing in a situation where you have a variable force between two isolated masses, which you don't usually really have, but it's a good first approximation. You know what to do with the variable force. You know how to calculate the average force. And this connects it all to the calculus. So, and I digress to this because somebody wrote it down in the integral form. And I want to clarify that the integral form gives you the same thing this does because of the connection between the integral and the average force. Just use that connection, it all works out. Now, again, in case of a collision, it's actually simpler to just express in terms of the average force, but you want to keep in mind how the average force is obtained because you do have problems when you have a force diagram. Okay, often you have kind of a Gaussian force. Okay, things collide, they make first contact, they're not compressed that much, there's not that much force. Then they compress a little more, and there's more force and more until they get maximum compression, so there's maximum force. And then the spring part force gradually decreases. The force curve looks like this in time. Probably not totally symmetric, there's hysteresis involved. I'm not going to worry about that right now. And not worry about it a whole lot for this situation. For this situation, we know there's an average force. We know that the average force is 3.0 opposite. Okay. So ignore this at your peril. I'm not going to ask you to do a sophisticated calculus derivation. I will maybe ask a problem where I give you a curve and ask you to estimate the average force. You want to at least have that picture. And then ideally you get your calculus skills up to where you really understand these connections. Okay. Okay. So in this collision, we know delta V1 and delta V2. Okay, so this tells us that immediately we find that M1 delta V1 equals negative F12 bar delta T and M2 delta V2 equals F12 bar delta T. And these are your changes in momentum. So this is delta P1. And this is delta P2. And we notice these are equal and opposite. So notice these are equal and opposite. It follows, it's not a fundamental principle, it follows from the impulse momentum theorem that delta P1 equals negative delta P2. And that, of course, means that if you have these two things that are equal and opposite, you get zero. It's a zero vector. Okay. I.e. conservation of momentum. I'll just say in an isolated system, this is an isolated system with just two masses. If you have an isolated system with more than two masses, well, the interactions are more complicated. Every mass interacts with every other one. Okay. So if you have 10 masses, you have 100, about 100 interactions to write down. You don't want to have to write it down. You just extrapolate it, use mathematical induction. Say, well, if it works for 10, it works for 11. Because that new one can just interact with the whole rest of the system and all that stuff. And you can extrapolate and derive conservation of momentum for the whole universe. Assuming that laws of physics don't change for the universe. And that, you know, James Webb Telescope is, among other things, sort of investigating that idea. Giving us data that allows us to investigate it. It's not really investigating anything. Give us the data, we analyze it. Or we get artificial intelligence to analyze it, which gets a little fuzzy because nobody knows what artificial intelligence is actually doing. We know how to set it up. We don't know what it does, but it gives good answers if we set it up right and analyze the results correctly. Okay, well, that's a whole other subject. Okay, so all this is involved in analyzing this. Well, what do you want to use is M1V1 plus M2V2 equals M1U1 plus M2V2, or whatever symbols you're used to seeing. Okay, you can invent your own. You have to use somebody else's symbols. That's kind of conventional. How does that come out of this? Well, what's the expression for delta V1? So They tell me what are delta V1 and delta V2? What are your expressions just in terms of V1, V2, U1, and U2 for your delta V's? Okay. So with this notation, what happened? Okay. Your delta V1 is going to be U1 minus V1. You subtract where you start from where you finish. And as I said, at least one person, it can be a little hard to figure out which order these things go in. Okay, but just ask yourself, if it's going faster afterwards than it's gone before, are we going to get a positive number or a negative number? We're going to get a positive change, right? If it ends up faster, the change is positive, so you'd better subtract the smaller one from the larger one. Okay? Try to, you can boil things down, no matter how complicated the formulas look, you boil them down to a simple question. Simple question is, well, what should my signs be here? Common sense, well, if it ends up going faster, we have to be positive. So it better not be V1 minus U1. Okay? Although that's not a bad answer at this point, because you can reverse it if you just think about what's being said. And then delta V2 is U2 minus V2. Okay, well, then in terms of M1 and delta V1 and M2 and delta V2, what's delta P1? And what's delta P2? Let's write that down. Okay, everybody did a good job of writing this down. So you understand what we're going to say here. The delta P1 is M1 delta V1, and that turns out to be M1 times this quantity. You distribute through by the M1, you get M1 U1 minus M1 V1. And delta P2 similarly is M2 U2 minus M2 V2. Every step of this is very, very simple. We just have to put them together in sequence, and we derive the formula everybody uses without understanding, although it's a good intuitive formula. So let's make sure we understand how the formula is connected to the impulse momentum theorem, which is the whole central idea of analysis of momentum. Okay, so delta P1 equals negative delta P2. And I've asked everybody to write that out, and I'm sure you've got it right. But just in case, I'll write it out, and then we're going to see where it leads. Okay, well, gee, let's see. How am I going to write this equals this? Well, no, this equals this, and this equals this. So just write down this equals a negative of this. So we get M1U1. M1V1 is a negative of M2 U2 minus M2 V2. Okay. Now, is that what you wrote down? I totally expect it is, but if you didn't, you can fix it. Okay. Okay, now I want to write this with the V's on one side and the U's on the other. So can you write this with the V's on one side and the U's on the other? Out of focus again. Yes. Okay. Wasn't recording again, but just quickly, we set this equal to this, we get this, and it's a very simple rearrangement to get this, which is what you're used to. M1V1 plus M2V2 equals M1U1 plus M2U2, or whatever notation you're using for the before and after velocities, V1A, V1B, whatever. Okay. That's very handy for the problem I gave you. But now you have a formula where you just plug everything in. And you also know that it's an inelastic collision, so U1 equals U2. It's also in one dimension, so you don't even need the arrows. Just make sure you have positive and negative signs and everything. So it becomes very easy to solve that problem. with this formula. Now, everybody went to formula. And pretty much solved it. Okay. Do you understand the formula? Do you understand the physics of what's really going on? Well, if you understand that momentum is conserved, that's a pretty intuitive idea. So you do understand something. Okay. Want to understand it a little more deeply. Another thing we get out of this analysis, and I think I can take this picture where we in focus. Don't know how long it's going to stay in focus, but the internet at the house keeps going in and out too. Y'all having that problem? Pretty unusual. It usually works pretty well. Today it's been pretty aggravating, and it went out yesterday, just for several minutes, and it comes back on for a while, and then it flips off. Of course, I got my security awareness training to do. Now that's been interact. It's overdue. Okay. If we take these relationships, you get something that's pretty intuitive. What's intuitive is, well, this equals the negative of this, so that just rearranging it, the delta V1 over delta V2 is inversely proportional to M2 over M1 over M2. Your changes in velocity are inversely proportional to your masses. And of opposite sign, if one speeds up, the other slows down. So that's why the negative sign's there. What this implies is greater mass implies less delta V. I think I used it. Shaquille O'Neal has about twice my weight. He's really slimmed down. I don't know if you've seen the picture. It's pretty impressive. A guy right now looks like a professional bodybuilder. Can you imagine that? 400 some pound guy down to 310 or something like that. Okay. So yeah, twice the mass. Okay, I run into Shaquille O'Neal. Not that I would do that because I don't want to hurt the guy. But I go take a running start, or maybe I get in a skateboard, put him in a skateboard, and we collide. Okay, who's going to win that collision? I am. I have half the mass. I get twice the change in velocity. I win. Now, which one is going to sustain more delta V? Well, it's going to be me. Which one's going to have more trauma out of the collision? Oh yeah, it's a guy that has greater delta V because of impulse momentum. Same delta T, twice as much average force. Maybe I don't. Depends what you call winning. Right? Okay. The point is, you can gain a lot of understanding about what goes on in collisions from this that you don't get from this. You can get it from this, but it's more obvious if you understand changes in momentum in the impulse momentum theorem. It's more direct. This is very handy. It's much more handy than having to go through all this every time you want to do it, but you want to have this available to you in case you need it. Because I almost guarantee you by the time I get done making up tests, you will. Okay. And it's going to be important for problems that you have for homework. Okay. So it's a big deal, which is why we spent an hour on it. And that's not what I planned to do. But from what I saw, I knew that we needed to spend the time on this. What I really want to do is look at the center of mass frame and the frames of reference. Okay, so how much have you seen about frames of reference? See anything about frames of reference? No? Okay, well, it's a really important idea that I don't think gets quite its due in the MyLab stuff. Because I'm going to understand elastic collisions if I got as a formula. Okay. Okay, so these things are moving, but wherever these things are, the center of mass is at the point. Center mass is here, provided this distance, we call this distance x, And then this distance is d minus x. Okay, this is x from M2, that's a distance d minus x from M1. Then M2 times x has to equal M1 times d minus x. Does that make sense? Well, the bigger mass, since M2 is bigger, then x has to be smaller here. The bigger mass has to be closer to the center of mass. So M2x is the product of the mass and the distance, and the product of the mass and the distance here turns out to have to be the same. Haven't derived that. We derived that from the work energy theorem. We'll get that. You don't want to deal with it now. Keep it intuitive. Okay, so intuitively, if this is twice as great, it's got to be twice as close. So if this is twice as great, x has to be half as much as d minus x. Okay, so it has to be twice as far. It has to be as this one. That's what this is expressing. We get it. M2x plus M1x equals M1d. Okay, you get this. Okay. Now, and I don't know why I have a minus there. That doesn't make any sense. If two masses were equal, then we'd have an infinite distance. Okay. I don't have time to put velocities in these things and see how it moves, but it comes down to this idea. If the collision is observed from the center of mass frame, in other words, if you're moving along with the center of mass, the collision looks different than if you're standing here. So you're driving along the road and two cars, hopefully at fairly low speed, so nobody gets hurt, collide, okay? Then if you're in the center of mass frame, you see these cars approaching with different velocities than you do if you see it from the side of the road. I wanted to go into a lot more detail on this. Okay. Observe from the center mass frame. it appears that the two masses end up stationary. Okay, now, two carts collide. I wanted to demonstrate this by putting magnets in the end of the carts and so forth, and maybe I'll do that next week, just briefly. Maybe we'll do that in lab, just to make this a week from the party, to make this clearer, okay? These things come together and then they move off with some common velocity. Observed from a frame moving at that common velocity, it looks like they come together and stay. If the collision is elastic, it looks like they come together and spring apart with the same relative velocity. So big deal here, I'll write it down. But you want to try to keep it in mind. Unfortunately, I wasn't able to develop it like I wanted to because we really needed to work through that other thing. The objects fly apart. Well, I'm going to say with U1 equal negative B1, U2 equal negative B2. Okay. In other words, they keep the same speed, but they reverse their direction. Any inertial reference frame, I didn't put the word inertial in here, but it means to be moving at constant velocity. From any frame, I'm not going to write it down. From any frame, the relative velocities remain the same. Okay. And I don't want to write it down without reasoning it out, because I want to make the connection. Look at your book and see what they tell you. Okay, what you to actually look at. We're over time. I don't want to take more time to do that explanation. Okay. And not sure the camera's even in focus. Focus the camera. Lady. Or stick around, you know. Do that video. Fill in the blanks there. Important concept, kind of a difficult one, but well worth understanding.
Back, I'm sorry.
Yep. Hold on,
I'm very
I
sorry.
just started recording. Okay, now I'd like you to look up and write down for any frame. If you're actually watching the video, I'm going to reward you. I didn't want to write it down for two reasons. I decided I wanted you to focus on it well enough to look it up and try to understand it. But the idea is simply that your relative velocity after collision is equal and opposite to your relative velocity before collision. So if the relative velocity, like you've been 40 miles an hour here and 60 miles an hour here, relative velocity if you're approaching is 100 miles per hour. Okay, I think I said miles per hour. And then after collision, it's going to be 100 miles per hour in the opposite direction. Now, what's that mean? Well, your relative velocity I could say more, but it changes sign. Okay, so what's the relative velocity before collision? Depending on which direction you take to be positive for the collision that we were looking at. Okay, V2 would have been negative, say V1 is positive. So you could say that the velocity of second mass relative to the first is V1 minus V2. Okay, so second mass, make sure I got this right. Second mass is doing 60 miles an hour this way. First mass is doing 40 miles an hour this way. Relative velocity, as I said, is 100 miles an hour. Okay, well, if I do 60, because that 60 is positive, the 40 is negative. So if I do 60 minus negative 40, I get 60 plus 40, that's 100 miles an hour. So that's the right expression for the relative velocity. After collision, the relative velocity is, again, the relative velocity of the second mass relative to the first would be U1 minus U2, and that has to be equal and opposite to this. Say the relative velocity changes sign. So that would be written down with a negative sign. Okay, so if you work that out and see what the velocity of M1 would be, the velocity of M2, and the U1 minus U2 after collision, it's not going to be the case in the inelastic collision. For an elastic collision, it would be the case, and this gives you a second equation to use along with your M1 U1 V1 plus M2 V2 plus M1 U1 plus M2 V2. So for an elastic collision, you would have this equation and the equation that we derived in graph. Yes. Now, the two equations you officially have for an elastic collision, you have conservation of kinetic energy. So you could write down 1/2 M1 V1 squared plus 1/2 M2 V2 squared equals 1/2 M1 U1 squared plus 1/2 M1 M2 U2 squared. You write out the whole expression for kinetic energy before and after, set them equal. You'd have two simultaneous equations that you could use. You'd be dealing with V squareds and U squareds, and it would be a lot more complicated, but you could solve those two equations for an elastic collision. Equivalently, you can just solve these two equations. It can be reasoned out from the center of mass frame in a way that, since we got hung up on connecting the impulse momentum theorem to the conservation of momentum equation, we didn't have time to get into in class. So right there is the whole ball of wax. Now, the other thing that we did in class, and I didn't record, and I wish I had a shorter meter sheet to do this with. Here we go. Let's see if I can do this without dropping them. Okay, I've got four dominoes here. And I just dropped the domino, and I'm gonna risk dropping everything by moving. Okay. If I want to balance this thing, where am I going to put the two dominoes? Well, I'm going to have to put them further from the balancing point or the fulcrum than these are. Okay, so maybe about here. Let's see how that does. I didn't put them far enough. I would have to put them too far because they'll go off the screen. Okay, put them about there. Let's see how that does. Yeah, still, okay, so I'm going to have to move my finger over a little bit. Okay, so there they balance pretty well. Okay. Now, if I move these an inch closer and move these 2 inches closer, because I've only got half the mass here. They should still balance. But maybe I moved that one too close. Okay, well, not sure this is a great demonstration, but you get the idea. Okay, I moved them closer. Okay, now if I move this one another, I move it half an inch closer, and move this an inch closer. They should still balance, but for some reason they don't, which is a little weird because I got this thing in the middle of the meter stick. Okay, it's just a question of, it's a little bit of a tough balance. Okay, now the point is, every time I move this closer and move this closer, I've got to move this twice as far as I move this because it's got half the mass. If these things aren't approaching such a way that this mass is moving twice as fast as this mass, then I'm not going to be able to balance it. My balance point's going to have to move. So if I move this twice as close and move this, or move this 2 inches closer and move this 3 inches closer, tends to balance this way. My center of mass is going to move to the left a little bit. My balancing point moves to the left. Okay. And if I move this another 3 inches closer, then this thing tends to tip over this way. I'm going to have to move this one, but I'm not going to move this one. I move this one only 1/3 that distance closer. My balancing point is going to continue moving to the left. So the center of mass of this system is now moving. Okay, well, that's what we mean by the center of mass of the system. And one reason that these things aren't working out is I've got 5 here and 2 here. So this has roughly 2.5 times the mass of this. So my numbers weren't working out right, and I didn't notice I had 5. It's a little past lunchtime, a little fuzzy. Okay, the point is that when 2 masses are approaching each other, the center mass doesn't necessarily, and it usually doesn't stay the same. Okay, it either moves this way or it moves this way. Hopefully the demonstration showed that. And if I had a table and a better setup was balancing things with my finger, it would show better, but I don't have time to set that up. So when we talk about center of mass frame, that's what we're talking about. We're talking about if we're moving along with the center of mass, the collision looks different than if we aren't. And I'm going to leave it to you to kind of work out the implications of that with some of the homework problems. And we'll be talking about it more in lab next week. Okay, so there it is.